Welcome to the Late Lab. It's lovely to have you here. Before tonight's quiet journey begins, where in the world are you watching from? Maybe tucked beneath a blanket, maybe half listening from a dim room, maybe sitting somewhere still while the rest of the day slowly loosens its grip. Wherever this finds you, may the next little while feel calm, comfortable, and gently curious. If these slow explorations help you relax, think, or drift a little closer to sleep, leaving a like and subscribing is a wonderful way to support the channel. And if you are already subscribed, thank you. Truly. It means a great deal, and it helps keep this small, sleepy corner of science glowing softly in the dark. Now, tonight's subject does come with a slight risk. It may make time itself seem a little less ordinary than it did a few minutes ago. But if that keeps the mind awake for a moment, at least it will be for a good reason. Learning how tiny atoms, quietly vibrating with quantum precision, help guide satellites, steady the internet, support power grids, and keep the modern world moving in step. So let's begin. Gently. What is quantum time, and how do atoms keep the modern world running? The modern world has a surprisingly delicate habit. It likes to pretend that everything is solid, organized, and sensible, when in reality it is quietly depending on billions of separate machines agreeing on the same invisible thing: time. Not time in the poetic sense, although that is lovely too. Not the kind of time that seems to stretch during a boring meeting and vanish mysteriously when someone sits down for 5 minutes with a cup of tea. This is time as infrastructure, time as coordination, time as the hidden rhythm that lets machines talk to each other, banks settle payments, satellites guide cars, power grids remain stable, laboratories compare measurements, and phones calmly tell people they are only 3 minutes late when the evidence suggests something slightly more dramatic. Every day, enormous systems depend on shared timing. A mobile phone needs time signals to connect properly with networks and satellites. Navigation systems need timing to calculate position. Financial systems need precise timestamps to know which transaction happened first. Power grids need timing to keep electrical waves aligned across large regions. Scientific laboratories need timing to compare results that may be separated by continents. Transport systems, communication cables, data centers, emergency services, and broadcasting networks all rely on clocks that are far more precise than anything most people ever think about. And that is the strange part. Time feels personal and familiar. It is the alarm in the morning, the kettle boiling, the train arriving, the message saying nearly there, which can mean anything from 2 minutes to a small geological era. But beneath that everyday experience is a much stricter version of time, a version measured so carefully that even tiny errors matter. For everyday life, an ordinary clock is usually good enough. A kitchen clock can be a minute wrong, and dinner will probably survive. A wristwatch can drift slightly and still be useful. Even a phone clock that updates itself invisibly gives the impression that time is simple. It appears politely in the corner of a screen. But scientific and technological timekeeping is very different. A tiny timing error can become a real problem when signals are travelling at the speed of light, when computers are exchanging information thousands of times per second, or when a satellite is trying to tell a receiver exactly where it is on Earth. Light travels roughly 300,000 kilometers in 1 second. That is about 7.5 times around Earth's equator in the time it takes to say the word second. So if a timing system is wrong by even a very small fraction of a second, the distance error can become large very quickly. This is why the most important clocks in the world are not simply better versions of familiar clocks. They are not grander pendulums, shinier gears, or more patient springs. The most precise clocks depend on atoms. That may sound like an odd solution. A clock built from atoms does not look like the kind of clock that belongs on a wall. There is no friendly face with hands going round. No tick-tock in the traditional sense. No little wooden bird bursting out each hour with more confidence than dignity. Instead, atomic clocks use one of the deepest facts discovered by quantum physics. Atoms absorb and emit energy in fixed, repeatable ways. Atoms are not vague little balls of matter with electrons wandering anywhere they please. In quantum physics, electrons inside atoms can occupy only certain allowed energy states. When an atom changes from one allowed state to another, the energy difference corresponds to radiation of a very specific frequency. That frequency is not chosen by human engineering. It is built into the atom's quantum structure. This makes atoms extraordinary timekeepers. A manufactured clock part can be slightly different from another manufactured clock part. A gear can wear down. A pendulum can expand with heat. A spring can weaken. A crystal oscillator can drift. But atoms of the same isotope are identical in a profound physical sense. A cesium atom of the right kind does not have a personal mood. It does not wake up feeling a little slower because it slept badly. It behaves according to quantum rules that are the same everywhere, as far as modern physics can measure. This is the foundation of quantum timekeeping. Scientists use atoms as natural references because the transitions between their energy states are stable, repeatable, and measurable. If a clock can be locked to one of these transitions, it can measure time with remarkable precision. The most important example is cesium-133. The modern definition of the second is based on a specific transition inside cesium-133 atoms. More precisely, it is tied to radiation, associated with a transition between two hyperfine levels of the ground state of that atom. Hyperfine structure comes from tiny interactions involving the magnetic properties of the atomic nucleus and the electrons around it. It is a delicate quantum detail, but it has become the foundation of civilized timekeeping, which is a rather grand career for something happening inside an atom. This definition is part of the International System of Units, the global measurement system used in science, engineering, trade, and technology. The organization that helps coordinate these standards internationally is the Bureau International des Poids et Mesures, based near Paris. Its name is French, because measurement standards, like pastries and diplomatic paperwork, have a long history in France. The Bureau International des Poids et Mesures helps maintain international agreement about units such as the meter, the kilogram, and the second. The second is no longer defined by Earth's rotation. That might seem surprising because days still feel like the most natural units of time. The sun rises, the sun sets, and the planet seems to provide a clock of its own. But Earth is not perfectly steady. Its rotation changes slightly because of tides, movements inside the planet, interactions with the moon, changes in the atmosphere and oceans, and other subtle effects. Earth is magnificent, but it is not a precision laboratory instrument. It wobbles, flexes, slows, and shifts. In cosmic terms, it is doing its best. Atomic time is steadier. By tying the second to cesium atoms, science moved the definition of time away from the irregular motion of a whole planet and toward the reliable behaviour of quantum systems. This does not make everyday time less human. It simply means that beneath ordinary clocks and calendars is a deeper standard, one that can be reproduced in laboratories around the world. That shared standard matters because modern civilization is a network of agreements. Machines need to agree on where they are, what happened first, when a signal was sent, when a record was created, and how different systems should stay synchronized. Time is not just a measurement, it is a form of trust. When a satellite navigation system gives a location, it depends on comparing the arrival times of signals from satellites high above Earth. When a financial exchange records trades, it depends on accurate timestamps. When a power grid monitors electricity across long distances, it depends on knowing the timing of electrical waves. When scientists compare measurements from different laboratories, they need confidence that their clocks are speaking the same language. So atoms do not merely help scientists measure time more neatly, they help hold together the hidden timing structure of the modern world. They sit quietly behind satellite navigation, communication networks, digital finance, energy systems, and scientific discovery. They are not visible in daily life, yet daily life increasingly depends on them. It is a beautiful reversal. The world of human technology feels huge. Cities, aircraft, cables under oceans, satellites circling Earth, data centers humming in carefully cooled rooms. But underneath it all, one of the most important foundations is tiny. A cesium atom changing state. A quantum transition repeating with astonishing regularity. A small physical rhythm, counted carefully enough, becomes the timing system of civilization. Every second feels ordinary because it arrives so smoothly. But that smoothness is not simple. It is maintained by instruments, laboratories, international standards, and the strange reliability of atoms. Modern life keeps moving because somewhere beneath the noise, the screens, the traffic, the messages, and the endless little demands of the day, quantum time is quietly keeping count. Long before time was defined by atoms, it was found in shadows. A person could look at the ground, watch the sun slide slowly across the sky, and see the day being drawn out in light and darkness. The earliest clocks did not tick, they stretched. A shadow lengthened, shortened, swung from one side to another, and gave human beings one of their first ways of dividing the day into something more manageable than morning, noon, and probably too late to start another important task. Sundials were among the simplest and most elegant timekeeping tools. A raised object called a gnomon cast a shadow onto a marked surface, and the changing position of that shadow revealed the passage of the day. They depended on a reliable truth. Earth rotates, and because of that rotation, the sun appears to move across the sky. Of course, the sun is not really circling over a sundial like a very punctual lantern. Earth is turning beneath it. But for practical human life, the effect was enough. The shadow moved, the day passed, and time became something that could be watched. The difficulty was that shadows are rather fussy employees. They refuse to work at night. They become vague in cloudy weather. They change with the seasons because the sun's path across the sky is higher in summer and lower in winter. A sundial can be wonderfully useful, but it is also tied to place, weather, latitude, and daylight. It is a clock that depends on the sky behaving politely. So human beings look for other ways to measure duration. Water clocks, also called clepsydras, use the steady flow of water from one container to another. Instead of relying on the sun, they relied on a physical process that could continue indoors, at night, or under cloudy skies. Ancient Egypt, ancient Greece, China, India, and other cultures used versions of water clocks for ritual, administration, astronomy, courts, and daily organization. A measured trickle of water became a way to divide time, although it still had problems. Water flow changes with pressure, temperature, vessel shape, and the cleanliness of the opening. Even a clock can be inconvenienced by sediment, which is a pleasingly humble reminder that civilization has often been troubled by small bits of dirt. Candle clocks and incense clocks offered another method. A candle could be marked along its length, and as it burned down it gave a rough indication of passing time. Incense clocks, used in parts of East Asia, could burn along prepared paths and sometimes trigger small sounds when threads burned through and dropped weights or balls. These devices turned combustion into measurement. They were not perfectly accurate, but they were useful, especially in contexts where people needed a gentle, visible, or audible sense of duration. In all of these early clocks, the same pattern appears. Human beings used the best regular process they could control: a shadow moving, water flowing, wax burning, incense smouldering. Timekeeping has always reflected the technology, materials, and scientific understanding of its age. A clock is never just a clock. It is a snapshot of what a culture knows how to make stable. For most of history, Earth itself was the great clock. A day came from Earth's rotation. A year came from Earth's orbit around the Sun. The phases of the moon shaped months in many calendars. The heavens seemed to provide a grand cosmic order, and for everyday life that order worked beautifully. Farmers, sailors, priests, rulers, astronomers, and ordinary families all depended on cycles in the sky. But Earth is not a perfect timekeeper. Its rotation is not absolutely constant. Tidal interactions with the moon gradually slow Earth's rotation over long periods. The atmosphere, oceans, and movement of material inside the planet cause smaller variations. Even the length of the day shifts slightly. The orbit around the Sun is also not a simple circle performed at a perfectly even speed. Earth follows an elliptical orbit, and its speed varies slightly as it moves around the Sun. The planet is wonderfully dependable for human life, but for precision measurement, it is a little too alive with motion. The rise of mechanical clocks changed the relationship between people and time. Instead of measuring time through flowing water or moving shadows, mechanical clocks used gears, weights, escapements, and later springs to create repeated controlled motion. Medieval mechanical clocks appeared in European towns and monasteries, where they helped organize prayer, labor, civic life, and public schedules. They were impressive machines, but early versions were not especially precise by modern standards. They could lose or gain significant time over a day. Still, they represented an important step. Time was being pulled away from nature and placed inside machinery. A major leap came with the pendulum clock. In 1656, the Dutch scientist Christian Huygens developed the first practical pendulum clock, using the regular swing of a pendulum to control the motion of the clock mechanism. The pendulum was a beautiful discovery for timekeeping because, for small swings, its period is highly regular. A pendulum transformed clocks from machines that roughly divided the day into instruments capable of much greater stability. But pendulums are not magic either. They depend on gravity, so their timing can vary slightly from place to place because Earth's gravitational strength is not exactly the same everywhere. They're affected by temperature, because the pendulum rod can expand or contract, changing its length. They're affected by air resistance, friction, and imperfections in the mechanism. A pendulum is wonderfully steady compared with earlier clocks, but it still belongs to the messy world of materials, forces, and workshop skill. The need for better clocks became urgent at sea. Latitude could be found using the height of the sun or stars, but longitude was far harder. To know longitude, a navigator needed to compare local time, found from the sky, with the time at a known reference location. The difference between those times revealed how far east or west the ship had travelled. The principle was simple. The practical problem was brutal. A ship at sea rolls, pitches, changes temperature, and moves through salty air. A pendulum clock on a ship is not a calm scientific instrument. It is more like a nervous guest at a dinner party during an earthquake. John Harrison, an English carpenter and clockmaker, devoted much of his life to solving this problem. In the 18th century, he built a series of marine chronometers, including the famous H4, that could keep time accurately enough at sea to make longitude measurement practical. Harrison's work was not just a triumph of clockmaking, It changed navigation, trade, naval power, and survival. A reliable marine chronometer meant ships could cross oceans with far better knowledge of their position. Timekeeping became a matter of life, death, empire, commerce, and the safe arrival of tea, spices, people, letters, and everything else that made the world increasingly connected. By the 19th and 20th centuries, clocks became steadily more precise. Mechanical clocks improved. Quartz clocks arrived, using the regular vibration of quartz crystals when electrically stimulated. Telecommunications, radio broadcasting, aviation, railways, and scientific experiments all required better synchronization. The world was becoming faster and more interconnected, and it needed time that could travel through wires, signals, schedules, and standards. Yet mechanical time and astronomical time were both reaching their limits. Earth's rotation was too irregular to serve as the ultimate standard. Mechanical systems were too dependent on materials and environment. Even quartz clocks, though excellent for many uses, still drift. The more precisely science measured the world, the more it needed a clock based on something deeper than a swinging object, a spinning planet, or a vibrating crystal. The search for time had always been a search for regularity. Shadows were regular enough for daylight. Water was regular enough for many ancient needs. Pendulums were regular enough to reshape daily life and science. Marine chronometers were regular enough to cross oceans. Quartz crystals were regular enough to support modern electronics. But each step revealed a quieter demand. Find something still more stable. That search eventually led away from the visible world of shadows, wheels, waves, and swinging rods, and into the invisible architecture of atoms. The next great clock would not depend on the turning Earth or a crafted mechanism. It would depend on quantum transitions, tiny changes inside atoms that repeat with extraordinary consistency. The history of timekeeping, in the end, is a story of humanity learning to trust smaller and smaller motions until the most reliable tick was no longer seen at all. Atoms make better clocks because they are not built in quite the same way that ordinary clocks are built. A mechanical clock is an achievement of craftsmanship. A quartz clock is an achievement of electronics and materials science. But an atomic clock leans on something more fundamental. It does not depend mainly on the shape of a gear, the tension of a spring, or the exact cut of a crystal. It depends on the fact that atoms, when carefully prepared and measured, behave according to rules that are astonishingly consistent. This is where quantum physics quietly enters the story. In everyday life, energy often seems continuous. A ball can roll a little faster or a little slower. A cup of tea can cool gradually. A pendulum can swing with a large arc or a smaller one. The world appears to allow smooth changes, but inside atoms nature is far more selective. Electrons in atoms cannot simply have any energy they like. They can occupy only certain allowed energy levels. These levels are discrete, which means they come in definite steps rather than forming one smooth range. That idea was one of the great shocks of early quantum theory. It suggested that the microscopic world was not just a smaller version of the familiar world. It had its own rules, its own structure, and its own stubborn refusal to behave like a tiny clockwork toy. Max Planck helped begin this revolution in 1900 when he proposed that energy could be exchanged in tiny packets, later called quanta. He was trying to solve a problem involving the radiation emitted by hot objects. But the idea opened a door that physics could not politely close again. Albert Einstein pushed the idea further in 1905 when he explained the photoelectric effect by suggesting that light itself could behave as if it came in packets of energy, now called photons. Then Niels Bohr introduced his model of the atom in 1913, proposing that electrons could occupy only certain orbits or energy states, and that light was absorbed or emitted when an electron moved between them. Bohr's model was not the final picture of the atom. Later quantum mechanics replaced its neat planetary orbits with wave functions, orbitals, probabilities, and a much deeper mathematical structure. But Bohr's central insight remains part of the story. Atoms have allowed energy states, and the changes between those states are linked to light of very specific frequencies. That is the key to atomic timekeeping. When an atom changes from one allowed state to another, it must absorb or emit exactly the right amount of energy. If the energy comes as electromagnetic radiation, such as microwaves or visible light, the radiation has a particular frequency. Frequency simply means how many cycles happen in a given amount of time. A slow wave has fewer cycles each second. A faster wave has more. In spoken terms, frequency is the rhythm of repetition. A clock needs a steady rhythm. That's all any clock has ever needed at its heart. A sundial uses the regular turning of Earth. A pendulum clock uses the regular swing of a pendulum. A quartz clock uses the regular vibration of a quartz crystal. An atomic clock uses the regular frequency associated with an atomic transition. In that sense, an atom can behave a little like a natural tuning fork. A tuning fork is designed to vibrate at a particular note. Strike it gently, and it rings with its own characteristic frequency. An atom also has characteristic frequencies, but they are not shaped by a metal prong made in a workshop. They are set by the atom's quantum structure. If the right kind of radiation is applied, the atom responds most strongly when that radiation matches the transition between two of its allowed energy states. This is not a vague similarity. Atomic clocks are built around this exact principle. They produce radiation at a controlled frequency, expose atoms to it, and look for the point where the atoms respond in the expected way. When the radiation matches the atomic transition as precisely as possible, the clock can lock onto that frequency and count its cycles. Counting those cycles gives a way to measure time. The beauty of this is repeatability. A pendulum can be made very well, but no two pendulums are perfectly identical. One rod might expand slightly more with temperature. One pivot might have more friction. One mechanism might age differently from another. Even quartz crystals, which are wonderfully useful, can vary because of manufacturing differences, temperature, stress, and long-term drift. Ordinary clock parts belong to the world of materials, and materials are always a little imperfect. Atoms are different. Every atom of the same isotope is identical in its fundamental properties. A cesium-133 atom in a laboratory in Paris is, in its basic quantum structure, the same as a cesium-133 atom in a laboratory in Colorado, Tokyo, London, or Braunschweig. It does not matter who prepared it, what country it is in, or whether the scientist operating the equipment has had enough coffee. The atom itself follows the same physical rules. This gives atomic clocks their extraordinary power. They do not rely on human beings manufacturing perfect objects. They rely on nature providing identical quantum systems. The task of the scientist and engineer is to isolate those systems, control their surroundings, reduce disturbances, and measure their behaviour as cleanly as possible. There is still plenty of engineering involved. Atomic clocks are not enchanted boxes into which atoms are placed so they can quietly behave perfectly while everyone goes home early. The atoms must be prepared carefully. The electromagnetic fields must be controlled. Temperature, magnetic fields, collisions, and technical noise must be understood and corrected. But the underlying reference is not a crafted object. It is a quantum transition. This is why atoms became the foundation of the modern second. The second is no longer defined by the swing of a pendulum or the turning of Earth. It is defined through the frequency associated with a specific transition in cesium-133 atoms. That means time is tied to a property of matter that can be reproduced anywhere with the right equipment. There is something quietly remarkable about that. Quantum physics is often introduced as the strange part of science, the realm where particles act like waves, measurements matter, and common sense starts looking around for the nearest exit. Yet this same strange theory gives us some of the most reliable patterns humanity has ever discovered. The quantum world is not unreliable because it is unfamiliar. In many ways, it is reliable precisely because its rules are so strict. An electron in an atom cannot casually choose a nearly correct energy level. An atomic transition does not drift because it feels like trying a new hobby. The allowed states are set by the structure of the atom and the laws of quantum mechanics. Once scientists learned how to use those transitions, they gained access to a kind of natural regularity far beyond ordinary machinery. So atoms make better clocks not because they tick in the familiar sense, but because they offer something deeper than a tick. They offer a repeatable frequency, rooted in the discrete energy levels of quantum physics. They turn the strangeness of the microscopic world into a practical rhythm for the human world. And this is one of the loveliest surprises in modern science. The same quantum rules that can make reality feel slippery, delicate and deeply unintuitive also allow civilization to measure time with almost unbelievable steadiness. Beneath the noise of machines, signals, satellites and screens, the modern second is anchored to tiny transitions inside atoms, repeating with a calm precision that no pendulum, planet or handmade mechanism could ever quite match. The atom that now defines the second is cesium-133, which sounds at first like a very specific answer to a question most people did not realize civilization was asking. Out of all the atoms in nature, why this one? Why should the rhythm of modern time be tied to cesium, a soft, silvery metal that most people will never see outside a laboratory? The reason is not that cesium is magical, although it has done rather well for itself. Cesium-133 has properties that make it unusually useful for timekeeping. It has one stable natural isotope, its atomic structure is well understood, and it has a microwave transition that can be measured with great precision. Most importantly, that transition is repeatable. A cesium-133 atom in one carefully built clock behaves like a cesium-133 atom in another carefully built clock, because the atom's basic quantum structure is the same everywhere. The key event happens inside the ground state of the cesium atom. The ground state is the lowest energy state of the atom, the state it naturally prefers when it is not being excited into something higher. But even this ground state is not completely simple. It is split into two very slightly different hyperfine energy levels. Hyperfine structure sounds intimidating, as if physics has put on a small waistcoat and become unnecessarily formal, but the basic idea can be made gentle. Inside the atom, the nucleus has magnetic properties, and the electrons around it also have magnetic properties. These tiny magnetic effects can interact with one another. Depending on how they line up, the atom can have slightly different energies, even within what would otherwise seem like the same basic state. The difference is extremely small, but small does not mean useless. In precision physics, small differences can become wonderfully reliable tools. The gap between the two hyperfine levels in cesium-133 corresponds to radiation at a very specific microwave frequency. When microwaves of just the right frequency interact with cesium atoms, the atoms are encouraged to shift between those two hyperfine states. This is the physical rhythm at the heart of the modern second. The current definition says that 1 second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. That is a large number, but it is not decorative. It is the exact number of cycles that defines 1 second. Instead of saying a second is some fraction of a day, modern science says a second is a fixed count of microwave radiation cycles linked to a specific quantum transition in cesium-133. The familiar second on a phone, oven, watch, or computer is therefore connected deep underneath to a quantum event inside an atom. This definition belongs to the International System of Units, the measurement system used internationally for science, engineering, medicine, industry, and trade. The Bureau International de Poids et Mesures, based near Paris, helps coordinate this global measurement system, including international time standards. The General Conference on Weights and Measures is the international body that makes formal decisions about the definitions of units. These organisations exist because measurement only works properly when everyone agrees what the units mean. A metre, a kilogram, and a second cannot be slightly different depending on local enthusiasm. A cesium atomic clock uses this definition in a practical way. It prepares cesium atoms and exposes them to microwaves. The clock adjusts the microwave frequency until the atoms respond most strongly, which happens when the frequency matches the cesium hyperfine transition. This matching point is called resonance. Once the clock has found that resonance, it can lock itself to the atomic transition and count the cycles of the microwave signal. In older cesium beam clocks, atoms moved through a carefully controlled apparatus, were exposed to microwaves, and were detected afterward to see how many had changed state. In modern cesium fountain clocks, atoms are cooled with lasers and tossed upward in a fountain-like path, giving scientists more time to measure them as they rise and fall. That longer measurement time improves precision, rather like listening to a musical note for longer, so its pitch can be judged more carefully. The important point is that the clock is not asking a gear or a spring to behave. It is asking an atom to reveal one of its natural quantum frequencies. The human-made machine still matters enormously. The microwaves must be controlled, magnetic fields must be managed. Temperature effects, collisions, and other disturbances must be corrected. But the heart of the measurement is not mechanical. It is quantum. This is why Earth's rotation eventually lost its role as the ultimate keeper of the second. Earth still gives us days, nights, seasons, and calendars, and it remains rather useful for things like standing on. But as a precision clock, Earth is imperfect. Its rotation changes slightly because of tides, motions in the atmosphere and oceans, and shifts inside the planet itself. The length of a day is close enough for ordinary life, but not stable enough for the most exact science and technology. Cesium gave science something steadier. It allowed the second to be defined by a property of matter that laboratories around the world could reproduce. A carefully built cesium clock in one country could be compared with another elsewhere. Not because the two machines were identical in every screw and cable, but because the atoms inside them followed the same quantum rules. So the official second is no longer a slice of Earth's turning. It is a count of atomic rhythm. That is a quiet but enormous change in human history. Time, once read from shadows and stars, is now defined by microwaves and hyperfine transitions. The second has moved from the sky into the atom, and the modern world keeps its pace by listening to cesium. By the middle of the 20th century, atomic timekeeping was no longer just a beautiful idea waiting politely inside quantum theory. It was becoming a machine. For decades, physicists had been learning that atoms were not vague little specks of matter, but structured quantum systems with precise energy levels. They could absorb and emit radiation at sharply defined frequencies. That made them seem like natural clocks, if only someone could build an instrument delicate enough to listen properly. The challenge was turning an invisible atomic transition into a practical device that could sit in a laboratory and measure time more steadily than the spinning Earth. This was the moment when quantum physics began moving from blackboards and spectroscopic measurements into precision engineering. It was one thing to know that atoms had stable transitions. It was another thing entirely to prepare atoms, send them through an apparatus, expose them to carefully controlled radiation, measure their response, reduce errors, and turn the whole process into a reliable clock. The result would not look like a familiar household clock. It would look more like a carefully arranged conversation between atoms, magnets, microwaves, detectors, and patient scientists trying not to breathe too enthusiastically near the equipment. One of the crucial figures behind this shift was Isidor Isaac Rabi. Rabi was an American physicist who developed powerful methods for studying atoms and molecules using molecular beams and magnetic resonance. In a molecular beam experiment, atoms or molecules are sent through a carefully controlled region, so their properties can be measured with great precision. Instead of studying a messy collection of particles moving in all directions, scientists could create a narrow beam and examine how those particles behaved when exposed to magnetic fields and electromagnetic radiation. Rabi's work showed that atoms and molecules could be probed with remarkable accuracy. Magnetic resonance allowed physicists to measure tiny differences in energy levels by finding the exact frequency at which particles responded. This was deeply important for atomic clocks, because a clock based on atoms must identify and maintain the right frequency. The whole idea depends on finding the natural quantum rhythm of the atom and locking the instrument to it. In 1944, Rabi suggested that atomic resonance could be used as the basis for a clock. That suggestion was not a casual remark. It was a sign that the atomic world had become precise enough to serve as a standard for time itself. If an atom responded to a particular frequency with extraordinary consistency, then that frequency could become a better reference than any mechanical motion or astronomical cycle. Another major figure was Norman Ramsay, who improved the measurement of atomic transitions with a technique known as the separated oscillatory fields method. The name may sound like something designed to make a sleepy listener gently reconsider their life choices, but the idea is elegant. Instead of exposing atoms to one continuous region of radiation, Ramsay's method exposed them to two separated interaction regions. This created a sharper and more useful measurement pattern, allowing scientists to determine the resonance frequency more precisely. Ramsay's method became central to high-precision spectroscopy and atomic clocks. It helped reduce uncertainty and improve the ability to identify exactly when the applied radiation matched the atomic transition. In the story of atomic timekeeping, this was not a small technical detail. It was one of the methods that made atomic clocks practical enough to challenge older standards of time. The first atomic clocks did not immediately begin with cesium as the final answer. Early work explored ammonia molecules and other systems, as scientists tested how molecular and atomic transitions could be used for timekeeping. These early devices were important stepping stones. They proved that atomic and molecular resonances could be used to regulate clocks, even if they were not yet the ultimate standard. The great practical breakthrough came at the National Physical Laboratory in the United Kingdom. There, Louis Essen and Jack Parry built the first practical cesium atomic clock in the 1950s. Their work focused on the microwave transition in cesium-133, the same atom that later became the foundation of the official definition of the second. In 1955, their cesium clock began operating with a level of stability that made it clear atomic timekeeping was not just possible, it was better. This was a turning point. For centuries, time had been tied to Earth and sky. The rotation of Earth defined the day. Astronomical observations helped maintain time standards. But as atomic clocks improved, they revealed something awkward about the old arrangement. Earth was not quite steady enough. Its rotation varied slightly. The planet slowed and shifted under the influence of tides, atmospheric motion, ocean currents, and internal changes. These variations were tiny, but atomic clocks could see them. That changed the direction of timekeeping. Instead of using astronomy as the final authority and clocks as imperfect copies of celestial time, scientists began to see atomic clocks as the steadier reference. Earth still gave human beings sunrise, sunset, and the rhythm of daily life, but the most precise version of the second would come from atomic physics. This shift was not only scientific, it was philosophical in a quiet, practical way. Humanity had once looked upward to the heavens for time, then it built machines to divide time more finely, then it looked inward into matter itself and found a rhythm more reliable than the planet beneath its feet. The official keeper of time moved from the sky to the laboratory, and then from the laboratory into the hidden infrastructure of modern life. The early atomic clocks were delicate, specialized, and far removed from ordinary experience. They belonged to national laboratories, not kitchen walls. They required controlled beams of atoms, precisely tuned radiation, magnetic shielding, vacuum systems, and careful measurement. Nobody was likely to glance at one and say, "Lovely, is it nearly lunchtime?" Yet these strange instruments became the ancestors of technologies that now support daily life in ways most people never notice. Satellite navigation, telecommunications, scientific measurement, financial timing, power grid monitoring, and global data networks all owe something to those early laboratory clocks. The path from Isidore Isaac Rabi's molecular beams to Norman Ramsay's separated oscillatory fields to Louis Essen and Jack Parry's cesium clock at the National Physical Laboratory is part of the hidden history of modern coordination. Atomic clocks began as fragile experiments built to test the precision of quantum transitions. They became the foundation of global time, and from those careful mid-20th century machines came a new kind of clockwork, not made of swinging pendulums or turning gears, but of atoms responding to microwaves with a steadiness that quietly outperformed the Earth itself. An atomic clock can sound, at first, like a tiny watch hidden inside an atom. It is a charming image. One can almost imagine electrons carrying little briefcases, arriving at work on time, ticking politely around the nucleus. But that is not really what happens. An atomic clock does not simply watch atoms tick, it tests them. At its heart, an atomic clock is a carefully controlled system built around a very simple question. What exact frequency makes these atoms respond? The answer to that question becomes the clock's rhythm. Instead of relying on a pendulum swing, a balance wheel, or a quartz crystal, the clock uses a quantum transition inside atoms as its reference. The atom provides the standard, and the machine is built to find that standard again and again with extraordinary care. The basic parts are easier to understand than the full engineering might suggest. First, there must be a source of atoms. In a cesium atomic clock, this means cesium-133 atoms. These atoms need to be prepared and guided into a region where they can interact with a controlled electromagnetic signal. In older cesium beam clocks, the atoms travel through the apparatus as a beam. In cesium fountain clocks, the atoms are cooled with lasers and gently launched upward, so they rise and fall through the measurement region. This gives the clock more time to observe them, which improves precision. Second, the clock needs a controlled electromagnetic signal. For cesium clocks, this signal is microwave radiation. The microwaves are tuned near the frequency associated with the transition between the two hyperfine levels of the cesium atom's ground state. The clock is not guessing wildly. It already knows roughly where the right frequency should be. But roughly is not enough when timekeeping is being pushed to national laboratory standards. The whole point is to find the closest possible match. Third, the clock needs a detection system. After the cesium atoms have interacted with the microwaves, The clock measures how many atoms have changed from one hyperfine state to the other. If many atoms have made the transition, the microwave frequency is very close to the atomic resonance. If fewer atoms respond, the frequency is not quite right. The atoms are, in effect, telling the machine whether it has found the correct note. This brings in the idea of resonance. Resonance is what happens when a system responds strongly to a particular frequency. A familiar example is tuning a radio. If the receiver is not tuned to the right frequency, the signal may be faint, noisy, or missing altogether. When it is tuned correctly, the station comes through clearly. Another comparison is a musical instrument. A guitar string, a tuning fork, or even a glass can respond strongly to a certain note. The right frequency does not merely nudge the system, it fits. Atoms have resonances too, but their resonances come from quantum energy levels. When the microwave frequency matches the energy difference between the two hyperfine levels in cesium-133, the atoms respond strongly. The atomic clock searches for that point of strongest response. It is not asking the atoms what time it is. It is asking very precisely, is this the frequency? Fourth, there is an electronic feedback loop. This is the part that keeps the clock locked to the atom. The machine continually checks the atom's response and adjusts the microwave frequency if needed. If the frequency drifts slightly too high or too low, the atoms respond a little less strongly. The feedback system notices this and corrects the signal. In this way, the clock steers itself toward the atomic transition, like a careful driver making tiny adjustments to stay in the lane. Once the microwave signal is locked to the cesium transition, the clock can count its cycles. A cycle is one complete repetition of the wave. If a signal repeats steadily, counting those repetitions becomes a way of measuring time. The modern second is defined by counting 9,192,631,770 cycles of the radiation associated with the cesium-133 hyperfine transition. That number is large, but the idea is simple. A stable repeating signal is counted, and that count becomes 1 second. This is how quantum behaviour becomes an ordinary clock readout. The user does not see atoms changing state. They see seconds, minutes, and hours. The quiet quantum work is translated into the familiar language of time. A display can show 3 o'clock, while deep inside the system, atoms and microwaves are engaged in an extremely precise conversation. To understand atomic clocks properly, it helps to separate 3 ideas that often get mixed together: stability, accuracy, and precision. Stability describes how consistently a clock runs over time. A stable clock does not wander around unpredictably. If it gains a tiny amount, it does so in a steady and understandable way, rather than behaving like a clock with personal drama. Accuracy describes how close the clock is to the true standard. A clock can be very stable but wrong. For example, it might gain exactly 1 second every day. That is stable, but not accurate. It is reliably incorrect, which is impressive in its own unhelpful way. Precision describes how finely a measurement can be made. A precise clock can distinguish very small intervals of time, but precision alone does not guarantee accuracy. A measurement can have many decimal places and still be wrong if the system is not properly calibrated. Atomic clocks aim for all 3: stability, accuracy, and precision, each supported by careful design and correction. This is why atomic clocks require such careful shielding and calibration. The atoms may be wonderfully consistent, but the world around them is not. Magnetic fields can shift atomic energy levels. Temperature changes can affect the apparatus and produce tiny changes in the measured frequency. Collisions between atoms can disturb the transition being measured. Electric fields, microwave imperfections, vibration, and electronic noise can all introduce errors. Even gravity matters, because clocks at different heights tick at slightly different rates according to general relativity. A good atomic clock is therefore not just a container full of obedient atoms. It is an entire environment designed to protect a measurement from everything that might blur it. Scientists work to reduce disturbances, measure the remaining effects, and correct for them. National metrology laboratories such as the National Institute of Standards and Technology in the United States and the National Physical Laboratory in the United Kingdom spend enormous effort understanding these tiny shifts, because tiny shifts are exactly where precision timekeeping lives. In the end, an atomic clock works by combining a natural quantum reference with human engineering. The atom supplies the repeatable transition. The microwaves test it. The detector listens for the response. The feedback loop keeps the signal aligned. The electronics count the cycles and turn them into seconds. It is not a little clock inside an atom. It is something subtler and more beautiful. It is a machine built around the reliability of nature at its smallest scale, using quantum structure to keep time for a world that never stops needing to know exactly when it is. Even the best clocks in the world are not perfect. That sounds almost unfair, because atomic clocks are among the most precise instruments ever made. They can keep time so steadily that some advanced clocks would gain or lose less than a second over timescales, far longer than the age of the universe, if all their conditions could remain ideal. They're astonishing machines. But astonishing is not the same as magical. Even an atomic clock still has to exist in the real world, which is always ready to interfere in small, creative and mildly inconvenient ways. The atom at the heart of an atomic clock may provide an exceptionally stable reference, but the atom must still be measured inside a machine. That machine has parts. It has fields. It has temperature. It has lasers or microwaves, electronics, detectors, vacuum chambers, and physical surroundings. It sits on Earth, inside gravity, near magnetic fields, in a universe that has not been designed specifically for the comfort of metrologists, although one suspects they have written several polite letters requesting improvements. This is why precision timekeeping is not simply about finding a perfect atom and declaring victory. The atom may be wonderfully reliable, but the measurement is always made through an instrument. Every instrument has limits. Every real clock has conditions that must be understood, reduced, corrected, or included in the uncertainty of the result. Uncertainty in measurement does not mean scientists are shrugging and guessing. It means there is a known limit to how exactly a measurement can be stated. A careful measurement includes not only the best answer, but also an estimate of how far that answer might reasonably be from the true value. In timekeeping, uncertainty is not a failure. It is part of honesty. It is how scientists say, very carefully, this is what the clock is telling us, and this is how well we understand what might be nudging it. There are two broad kinds of imperfections that matter in atomic clocks. One is systematic error. The other is random noise. A systematic error is a predictable shift caused by something in the clock's environment or operation. It pushes the measured frequency in a particular direction. If scientists can understand it, they can correct for it, or include it in the clock's uncertainty. Temperature is one example. Even a carefully controlled laboratory is not free from thermal effects. Warm objects emit radiation, and that radiation can shift atomic energy levels slightly. This is known as a blackbody radiation shift. It is tiny, but tiny is exactly where atomic clock science lives. Magnetic fields can also shift atomic energy levels. Atoms are affected by magnetism because their electrons and nuclei have magnetic properties. If an unwanted magnetic field is present, it can change the frequency of the transition being measured. Atomic clocks therefore need shielding, careful field control, and repeated checks. It is rather like trying to hear one exact note in a room where several invisible orchestras may be tuning up very quietly in the distance. Electric fields can cause shifts too. Motion matters as well. If atoms are moving, their interaction with radiation can be affected by Doppler shifts. The same broad effect that changes the pitch of a siren as it moves toward or away from an observer. In atomic clocks, scientists work extremely hard to reduce and control atomic motion. In modern fountain clocks and optical clocks, laser cooling can slow atoms dramatically, bringing them close to absolute zero so their movement becomes far less disruptive. Gravity adds another layer. According to Albert Einstein's general theory of relativity, clocks run at different rates depending on gravitational potential. A clock at a higher altitude ticks very slightly faster than a clock lower down, because it is in a weaker gravitational field. For ordinary life, the difference is far too small to notice. For the best atomic clocks, it matters. Raise an extremely precise clock by a small height, and the difference can become measurable. Timekeeping has become so exact that the height of the clock above Earth must be considered. The flaw, in other words, has joined the conversation. Then there are collisions between atoms. If atoms interact with one another during measurement, their energy levels can be shifted. This is especially important when many atoms are used together. Scientists may reduce the number of atoms, control the density, or measure how the result changes under different conditions so they can correct for the effect. Even in a vacuum, perfect isolation is difficult. Nature rarely hands over a measurement without adding a small footnote. Random noise is different. It is not a steady push in one direction, but short-term jitter. If the same clock measures the same transition again and again, the results may vary slightly from one measurement to the next. This can happen because of technical noise in electronics, fluctuations in lasers or microwaves, detector limits, vibration, or the basic statistical behaviour of measuring a finite number of atoms. The clock may be working beautifully, but individual readings still scatter a little. Random noise can often be reduced by averaging many measurements. If the noise is truly random, longer observation helps the stable signal emerge more clearly. This is one reason clock performance is often discussed over different averaging times. A clock might be excellent over a second, better over an hour, and astonishing over a day. Stability is not just about one moment. It is about how a clock behaves as time passes. The distinction between systematic error and random noise is important because they are handled differently. Random noise can often be smoothed out with repeated measurements. Systematic errors must be identified and corrected. A clock that is noisy may become clearer with patience. A clock with an uncorrected systematic error may remain confidently wrong for a very long time, which is a quality best admired from a safe distance. National metrology institutes exist to understand these problems at the highest level. The National Institute of Standards and Technology in the United States develops and operates some of the world's leading atomic clocks. The National Physical Laboratory in the United Kingdom has a long history in timekeeping, including the first practical cesium atomic clock. The Physikalische Technische Bundesanstalt in Germany is another major centre for precision measurement and time standards. Around the world, other national metrology institutes compare clocks, refine methods, measure uncertainties, and contribute to international timekeeping. These institutes do not simply build clocks and trust them. They compare them. They test them under changing conditions. They search for hidden biases. They ask whether a magnetic field is slightly wrong, whether a laser frequency is drifting, whether the temperature has been measured well enough, whether gravity has been accounted for, whether the atoms are interacting, whether the electronics are adding noise, and whether the clock is quietly misbehaving in a way that has not yet been noticed. This is the real pursuit of better timekeeping. It is not the search for a clock that is perfect in some absolute effortless sense. It is the search for a clock whose imperfections are understood so deeply that they can be reduced, corrected, and honestly described. The better the clock becomes, the smaller the remaining errors become, and the harder scientists must work to find them. There is something almost calming about that. The most precise clocks in the world are not perfect objects floating above reality. They are real instruments, made by real people, sitting in real laboratories, surrounded by a universe full of tiny influences. Their greatness comes from the fact that those influences are not ignored. They are studied. Atomic timekeeping is therefore a quiet discipline of humility. It begins with the remarkable regularity of atoms, but it continues through shielding, cooling, calibration, comparison, and correction. Every improvement comes from noticing another small reason time might slip, then finding a way to measure it more clearly. Perfect time may never quite be perfect, but by understanding every tiny reason a clock can drift away from perfection, science has built timekeeping so steady that the imperfections themselves have become tools for discovery. No single clock rules the world. That may seem surprising, because modern time can feel as if it comes from one invisible master clock somewhere, ticking away with immense authority while every phone, computer, satellite, railway station, and microwave oven politely obeys. But global time is not maintained by one lonely machine sitting in a sealed room, looking smug and faintly overqualified. It is built from many clocks, in many places, compared and combined through international cooperation. The world's most important time standards are created from an invisible agreement between laboratories. National metrology institutes operate atomic clocks, often including cesium clocks, hydrogen masers, and increasingly advanced optical clocks. These clocks are measured, compared, and reported. Their data is gathered and processed so the world can maintain a shared timescale. In other words, global time is not the voice of one clock. It is more like a carefully conducted choir, except the singers are atoms, and nobody is allowed to be even slightly out of tune without paperwork. This matters because every clock, even a very good atomic clock, has small imperfections. One clock may be extremely stable over short periods, another may be better over longer periods. One may drift slightly in a way that is understood and corrected, another may be affected by a local environmental condition. By comparing many clocks, scientists can create a time standard more reliable than any single instrument on its own. The strength comes from the network. One of the central ideas in this system is international atomic time. International atomic time is a continuous atomic timescale calculated from data contributed by atomic clocks around the world. It is designed to be steady and uninterrupted, based on the combined performance of many clocks rather than the behaviour of Earth's rotation. It does not pause to adjust itself to the slightly irregular turning of the planet. It is the clean, continuous rhythm of atomic time, built from quantum measurements and careful comparison. The organisation responsible for calculating international atomic time is the Bureau International des Poids et Mesures, based near Paris. The Bureau International des Poids et Mesures collects timing data from national laboratories and combines that information to maintain international timescales. These laboratories include institutions such as the National Institute of Standards and Technology in the United States, the National Physical Laboratory in the United Kingdom, the Physikalische Technische Bundesanstalt in Germany, and many other national metrology institutes around the world. The Bureau International des Poids et Mesures does not simply pick a favourite clock and tell the others to try harder. It analyses the performance of many clocks, compares them, assigns weight based on their reliability, and produces a coordinated timescale. This is a deeply technical process, but the principle is gentle enough to understand. If many excellent clocks are watched carefully, their combined behaviour can reveal a better estimate of time than one clock alone. Then there is coordinated universal time, the timescale used as the basis for civil time around the world. Coordinated universal time is closely related to international atomic time, but it has an additional responsibility. It must remain reasonably aligned with Earth's rotation, because human life is still connected to the day and night cycle. People may live in a world of atomic clocks, but nobody wants noon slowly wandering into the middle of the night simply because atoms are being impressively consistent. This is where leap seconds come in. Earth's rotation is not perfectly steady. It changes slightly because of tidal interactions with the moon, motion in the atmosphere, ocean currents, changes inside Earth, and other subtle influences. Atomic time, by contrast, is far more uniform. Over time, these two ways of keeping time can drift apart, the smooth atomic timescale and the slightly irregular rotation of the planet. Leap seconds were introduced to keep coordinated universal time close to the time based on Earth's rotation. When the difference between atomic time and Earth rotation time grows too large, an extra second can be added to coordinated universal time. This keeps civil time linked to the astronomical day. It is a small correction, but it has large practical implications because computer systems, communication networks, satellites, and financial systems all need to handle time changes correctly. A leap second sounds simple. Add 1 second and carry on. But in modern technology, even 1 extra second can be awkward. Computers prefer time to move in a smooth, predictable sequence. Networks, databases, and distributed systems can become confused if a second appears in a way they were not designed to handle. For this reason, the future of leap seconds has been debated internationally. The question is not whether Earth's rotation is changing. It is how much modern civil time should continue adjusting itself to follow that change. This debate shows something important. Timekeeping is not only physics, it is also agreement. At the deepest level, the second is tied to quantum behaviour in atoms. But the time used by society also has to serve people, technologies, governments, navigation systems, communication networks, and scientific institutions. It must be physically precise and socially usable. That is a delicate balance, and like many delicate balances, it becomes more impressive the less anyone notices it. To compare clocks across the world, laboratories use time transfer methods. A clock in one country cannot simply be placed next to a clock on another continent unless someone is planning an extremely inconvenient laboratory visit. Instead, scientists compare clocks using satellite links, radio signals, fibre optic connections, and specialized timing networks. Signals can be sent between laboratories or through satellites, allowing researchers to measure differences between clocks separated by oceans and continents. Satellite time transfer has long been central to international clock comparison. Global navigation satellites, communication satellites, and dedicated methods allow laboratories to compare their local clocks with others around the world. Increasingly, optical fibre links are also used for extremely precise comparisons over land. Fibre networks can transfer frequency and timing signals with remarkable stability, allowing clocks in different laboratories to be compared as if they were part of one extended instrument. This is how global time becomes possible. Atomic clocks generate highly stable local time. National laboratories maintain and study those clocks. Time transfer methods compare them. The Bureau International de Poids et Mesures combines the data. International atomic time provides a continuous atomic scale. Coordinated universal time gives the world a practical civil time closely connected to atomic precision, and, where necessary, Earth's rotation. It is a quiet form of international cooperation that most people never think about. And that is probably a sign that it works. When someone checks their phone, catches a train, sends a payment, follows a map, watches a live broadcast, or joins a video call, they are not usually thinking about atomic clocks, satellite links, or the Bureau International de Poids et Mesures. They are simply trusting that time is there, steady and shared. But modern time is not just there. It is made. It is maintained through quantum measurements, careful correction, and agreement between laboratories across the planet. It is built from atoms, mathematics, engineering, satellites, institutions, and a great deal of patient comparison. The world keeps time not because one clock commands it, but because many clocks are listened to together, and that makes quantum time even more remarkable. The modern second begins with tiny transitions inside atoms, but it becomes global only through human cooperation. It is nature's rhythm turned into an international language. Somewhere beneath the ordinary clock on a screen is an invisible agreement, stretched across laboratories and continents, allowing the modern world to keep moving in step. Satellite navigation feels almost effortless. A phone opens a map. A small blue dot appears, and the world seems to know where you are. It may even know this with slightly unsettling confidence, especially when it insists you are standing inside a building next door. But beneath that simple dot is one of the most precise timing systems ever built. Satellite navigation works by measuring time. A receiver on Earth, such as a phone, car navigation unit, ship system, aircraft system, or surveying instrument, listens for signals from several satellites. Each satellite sends information that includes where the satellite was and when the signal was sent. The receiver compares the arrival times of those signals. Because radio signals travel at the speed of light, the travel time reveals distance. If the receiver knows how far it is from several satellites at once, it can calculate its position on Earth. The principle is elegant, but the timing has to be extremely precise. Light and radio signals travel at about 300,000 kilometers per second. That means a tiny timing error becomes a large distance error very quickly. A difference of just 1/1,000,000th of a second corresponds to roughly 300 meters of signal travel. That is not a small mistake if someone is navigating a ship through a harbour, landing an aircraft, mapping a construction site, or trying to find a cafe that is supposedly just around the corner, a phrase with a long history of betrayal. This is why satellite navigation systems depend on atomic clocks. The satellites need stable timekeeping on board, and the ground systems need to know exactly how those clocks are behaving. The most familiar system is GPS, the Global Positioning System, operated by the United States. But it is not the only one. Galileo is operated by the European Union, GLONASS is operated by Russia, Beidou is operated by China. Together, these systems form the wider family of global navigation satellite systems, and all of them rely on precise timing, atomic clocks, and coordinated ground control. Each navigation satellite carries atomic clocks because its signal must be time-stamped with great accuracy. If the satellite's clock drifts, the receiver's distance estimate becomes wrong. And because position is calculated from several distance estimates at once, timing errors can ripple through the whole solution. The receiver is not directly measuring distance with a tape measure stretched into orbit, which would be ambitious and difficult to store in a drawer. It is measuring signal travel time. Time is the ruler. The clocks on satellites are not simply launched into space and left to behave perfectly forever. Ground. Stations continuously monitor the satellites, compare their signals with reference time standards, and send corrections when needed. These ground control networks track satellite orbits, check clock performance, and keep the system aligned with global time. Satellite navigation is therefore not just a collection of objects circling Earth. It is a coordinated system of space hardware, ground stations, atomic clocks, mathematical models, and constant correction. And then there is relativity. Albert Einstein's special theory of relativity and general theory of relativity are not optional decorations in satellite navigation. They're essential. Special relativity says that moving clocks tick at different rates compared with clocks that are relatively at rest. Since navigation satellites move rapidly around Earth, their clocks are affected by their motion. General relativity says that gravity also affects time. A clock deeper in a gravitational field ticks more slowly than a clock higher up in a weaker gravitational field. Satellites orbit far above Earth's surface, where gravity is slightly weaker, so their clocks tick differently from clocks on the ground. These two effects do not cancel perfectly. The satellite's motion tends to make its clock run slower relative to Earth, while the weaker gravity at orbital altitude tends to make it run faster. The gravitational effect is larger for navigation satellites, so overall their clocks run slightly faster than comparable clocks on Earth. The difference is tiny in daily human terms, but for satellite navigation it is enormous. If relativity were ignored, position estimates would drift by kilometers over time. This is one of the clearest examples of advanced physics quietly supporting ordinary life. The same theories that describe time changing with motion and gravity are built into the operation of satellite navigation. Without relativistic corrections, map apps would not simply be a little off. They would become very confident liars, guiding people with impressive certainty toward places they did not intend to visit. So whenever someone checks a route, tracks a parcel, follows a hiking trail, lands an aircraft, guides a tractor across a field, synchronizes a telecom network, or finds the nearest coffee shop with suspiciously good accuracy, two great pieces of physics are working together. Atomic transitions provide the steady rhythm of quantum time. Relativity explains how that rhythm changes when clocks move through space and sit at different heights in Earth's gravitational field. It is a beautiful partnership. Quantum physics gives the clock its precision. Relativity tells the clock how space, motion, and gravity affect its ticking. Engineering turns both into a usable system, and modern life receives the result as a small dot on a screen, gliding calmly through streets, fields, oceans, and skies. The dot feels ordinary because the technology is hidden, but every accurate position depends on tiny intervals of time being measured, corrected, and trusted. Satellite navigation is not really a machine that knows where things are. It is a machine that knows when signals arrived with astonishing care. From that careful timing, the world finds its place. The internet can feel as if it happens all at once. A message is sent, a page loads, a video begins, a payment goes through, a voice call crosses continents, and everything appears almost immediate. The experience is smooth enough that it's easy to imagine the internet as a kind of weightless cloud, where information simply appears wherever it is needed. But underneath that smoothness is a world of strict order. Signals have to be sent, packets of data have to be routed, records have to be stamped, machines have to agree on what happened first, and for that, the internet needs time. Computer networks are not just pipes carrying information, they are systems of coordination. Servers, routers, switches, satellites, cables, data centers, phones, laptops, payment systems, and security services all need some shared sense of time to organize their work. Without reliable timing, digital systems can become confused in subtle but serious ways. A file update might appear to happen before the file existed. A transaction might arrive out of order. A security certificate might seem expired when it is not. A data center might struggle to decide which copy of information is the newest. This is especially important because the internet is distributed. There is no single machine politely holding all the information and making every decision on behalf of everyone else. Instead, many machines work together across cities, countries, and oceans. They send each other small packets of information, store copies, verify identities, balance workloads, and keep services running even when parts of the system fail. Shared time helps these separate machines behave as if they are part of one coordinated whole. One of the most common tools for this is the network time protocol. The network time protocol allows computers to compare their local clocks with more reliable time sources across a network. A computer sends a request, receives a response, estimates how long the message took to travel, and adjusts its own clock accordingly. It is not perfect, because networks have delays that can vary from moment to moment, but it is good enough for many ordinary uses. It quietly keeps laptops, servers, and devices close to the correct time. For systems that need tighter control, there is the Precision Time Protocol. The Precision Time Protocol is used where more accurate synchronization is needed, especially in industrial systems, telecommunications, finance, broadcasting, and power networks. It works by carefully measuring timing differences between a master clock and other devices on the network. In well-designed systems, it can synchronize machines far more closely than ordinary internet time methods. The names may sound dry, but the purpose is surprisingly human. These protocols are ways for machines to ask one another, "What time do you think it is?" and then gently correct themselves. It is a digital version of everyone in a room checking their watches, except the room is planet-sized, the watches are servers, and the conversation is happening through cables, radio links, and fiber optic networks. Reliable timing matters in finance because trades, transfers, and payments must be recorded in the correct order. Financial trading systems can operate across extremely short intervals, and regulators need accurate timestamps to reconstruct what happened. If events are not ordered properly, trust begins to wobble. Money is not just numbers, it is a sequence of authorized events, and sequences need time. Telecommunications also depends on timing. Mobile phone networks, fiber optic systems, and data networks must coordinate signals so that information arrives where it should, when it should. If timing slips, performance can degrade. Calls may drop, data may be delayed, and network equipment may struggle to coordinate. A modern phone network is not just a crowd of devices shouting into the air. It is a carefully timed system, with signals arranged so they do not all trip over one another like guests arriving through the same doorway at once. Cloud computing adds another layer. Large data centers contain thousands or even millions of machines working together. They divide tasks, store data, mirror information, authenticate users, and recover from failures. Timestamps help them decide which events happened in which order. They help databases maintain consistency. They help logs make sense when engineers need to diagnose a problem. If a service fails, accurate time records can reveal the chain of events that led to the failure. Without trusted time, the story becomes muddled. Video streaming also relies on timing. Audio and video must remain synchronized. Packets arrive in pieces and are reassembled into smooth motion and sound. Live broadcasts require timing to coordinate cameras, encoders, servers, networks, and playback devices. When it works, a person simply watches a video. When it fails, the mouth moves and the sound arrives late, which makes everyone appear briefly dubbed by a slightly distracted ghost. Emergency services need reliable timing as well. Dispatch systems, communication networks, location services, radio systems, and incident records all depend on accurate coordination. In critical situations, knowing when a call arrived, when a unit was dispatched, when a location was updated, and when a response began can matter greatly. Time is part of accountability, safety, and coordination. Power grid control also depends on timing, especially as electrical networks become more complex. Grid operators monitor frequency and phase across wide regions. Devices such as phasor measurement units compare the timing of electrical waves at different points in the grid. To make those comparisons meaningful, they need accurate time references. A tiny timing difference can reveal how power is flowing and whether part of the grid is becoming unstable. Behind all of this are time references supported by atomic clocks. National laboratories maintain highly accurate time standards. Telecommunications infrastructure may use atomic clocks, satellite timing, and disciplined oscillators to keep networks aligned. Servers and network operators often trace their time back through layers of equipment and protocols to highly stable sources connected to atomic time. Satellites, including navigation satellites, also distribute precise timing signals used by many systems on Earth. The important point is that digital systems may feel instant, but they are not timeless. They are built from strict sequences of events. A message leaves before it arrives. A transaction is requested before it is approved. A file is changed before it is copied. A signal is sent before it is received. Timestamps are the labels that help machines understand those sequences. They turn digital activity into an ordered history. Quantum timekeeping hides beneath this ordinary internet life. The user sees a notification, a payment confirmation, a streamed film, a map update, a call, a search result, or a saved document. Beneath that surface are clocks being compared, corrected, and trusted. Beneath many of those clocks are atomic transitions, the quiet quantum rhythms that help define the second itself. So the internet is not only made of cables, satellites, servers, and code. It is also made of agreement about time. Every smooth connection depends on countless small acts of synchronization. Messages arrive in order, accounts balance, machines decide what happened first, and somewhere behind the screen, far from the casual tap of a finger, atoms help the digital world keep its place in time. Money may seem, at first, like a thing made of coins, notes, cards, numbers, promises, and the faint emotional weather that arrives when checking a bank balance after a holiday. But in the modern world, money is also made of time. Every payment, trade, transfer, settlement, refund, fee, balance update, and market order has to happen in an order that can be trusted. It is not enough for a financial system to know that several events occurred. It has to know which event happened first, which came next, and which record should be treated as the valid one. In a world where money moves through networks at extraordinary speed, timestamps are not decorative labels. They are part of the structure that makes the system understandable. A timestamp is simply a record of when something happened. But in finance, that simple idea becomes extremely important. If a person taps a card in a shop, the payment system needs to record the request, authorization, clearing, and settlement. If a bank transfer is made, the system needs to know when the instruction was received, when it was processed, and when the funds moved. If a stock trade occurs, the exchange needs to know exactly when the order arrived and when it was executed. These events may appear almost instant to the customer, but underneath them is a careful sequence. Modern financial systems are distributed across many machines and institutions. Banks, payment processors, stock exchanges, clearing houses, card networks, trading platforms, regulators, and data centers all keep records. Those records only make sense when they are linked to reliable time. If two systems disagree about timing, the order of events can become unclear. And when the order of events involves money, ownership, contracts, or legal responsibility, confusion is not charming. It is expensive. High-speed trading makes this especially clear. In financial markets, Some trading systems operate over extremely small intervals of time. Orders can be sent, cancelled, matched, or routed in tiny fractions of a second. This does not need to be treated like a science fiction battle between machines in a glowing digital arena. It is more grounded than that, although still rather intense. The important point is that when market activity happens very quickly, accurate timing is essential for knowing what actually occurred. A trading venue may need to know when an order entered the system, when it was matched, when a price changed, when market data was published, and when a participant received that information. Even tiny differences can matter when reconstructing events. If several orders arrive very close together, timing helps determine priority. In many markets, the order in which instructions arrive can influence whether a trade happens, at what price, and under what conditions. This is why financial regulators care about traceable time. Traceable time means that a clock used in a system can be connected back through a known chain of comparisons to an official time standard. The clock is not merely trusted because it looks confident. It is trusted because its relationship to a recognized timescale can be demonstrated. Regulation often requires financial firms, trading venues, and other market participants to synchronize their clocks within defined limits. The exact requirements vary by country, market, and system, but the principle is the same. If something goes wrong, investigators need to reconstruct the sequence of events. They need to see which orders were submitted, which trades occurred, which systems responded, and when each step happened. Accurate timestamps help detect errors, resolve disputes, investigate suspicious activity, and maintain accountability. Without reliable timing, a financial record can become a pile of events with the pages shuffled. The information may still be there, but the story is harder to read. In calm conditions, this might be inconvenient. During fast market movement, technical failure, fraud investigation, or legal dispute, it can become a serious problem. Banks also depend on timing in less dramatic but equally important ways. A bank must process deposits, withdrawals, transfers, interest calculations, card transactions, direct debits, standing orders, and account updates in the correct sequence. Payment networks need to coordinate messages between merchants, card issuers, acquiring banks, processors, and settlement systems. Clearing systems need to reconcile obligations between institutions. Stock exchanges need to match buyers and sellers. Clearing houses need to reduce risk by ensuring that trades are properly recorded and settled. All of this depends on coordinated digital records. A balance is not just a number floating peacefully in a database. It is the result of a history. Money came in, money went out, payments were authorized, transfers cleared, fees were applied, interests may have been added, and records were updated. If the timing of those events is wrong, the balance may become difficult to explain. And a financial system that cannot explain its own balances is not having a small personality quirk. It is in trouble. For most people, this hidden timing work appears as a simple experience. A card is accepted, a transfer arrives, a payment confirmation appears, a balance updates, a salary lands, a subscription leaves with suspicious punctuality. The system feels ordinary because the coordination is hidden. But behind that ordinary moment, clocks are helping different machines agree on the sequence of events. Atomic time supports this trust indirectly but powerfully. National laboratories maintain time standards based on atomic clocks. Telecommunication systems, satellite timing services, data centers, and financial infrastructure can trace their time back to these standards through networks of comparison and synchronization. The chain may involve satellite signals, fiber optic links, network timing systems, local reference clocks, and disciplined oscillators, but the deeper foundation is the same. Modern time is anchored to atomic precision. This connects finance to the wider hidden clockwork of the internet. Money now moves as information, and information needs ordering. A payment network is not so different from any other distributed digital system in this respect. Messages must be sent, received, verified, recorded, and reconciled. Machines must agree on what happened first. When millions of people are buying food, paying bills, trading shares, sending salaries, moving savings, and tapping cards, the system needs more than trust in numbers. It needs trust in sequence. That is the quiet role of quantum time in modern finance. It does not make money fairer, wiser, calmer, or less likely to vanish mysteriously after one quick online shop. But it helps make the records coherent. It helps institutions compare events. It helps regulators investigate what happened. It helps markets and payment systems keep their digital histories in order. Money is one of the clearest examples of modern coordination. It depends on agreement about value, ownership, obligation, identity, and order quietly needs clocks. Beneath the simple moment of a payment going through, beneath the flicker of a transaction on a screen, there is a deeper rhythm of synchronized time. Somewhere behind the banks, networks, exchanges, and records, atomic clocks help the financial world remember not just what happened, but when. Electricity feels instant because for most people, it arrives without ceremony. A switch is pressed, a room fills with light, a kettle begins its small domestic roar, a computer wakes, a phone charges, a fridge hums quietly in the background, doing its noble work of protecting cheese. The power grid feels like a simple promise. Ask for electricity, and electricity appears. But behind that ordinary promise is a vast timing problem. Electrical power grids are not just collections of wires, carrying energy from generators to homes. They're enormous synchronized systems. In many parts of the world, the electricity delivered through the grid is alternating current, which means the voltage and current rise and fall in a repeating wave. That wave has a frequency. In many countries, the grid frequency is 50 cycles per second. In others, including the United States, it is 60 cycles per second. The exact value depends on the region, but the principle is the same. The grid must maintain a steady rhythm. That rhythm matters because generators, transmission lines, transformers, industrial equipment, and household devices are all connected through the same electrical dance. If supply and demand fall out of balance, the frequency can shift. If too much electricity is demanded and not enough is supplied, frequency can drop. If supply becomes too high for demand, frequency can rise. These changes are usually tiny and carefully controlled, but if they grow too large, they can damage equipment or trigger protective systems that disconnect parts of the grid. Grid operators spend their days keeping this balance steady. They monitor generation and demand, adjust power sources, coordinate reserves, respond to faults, and manage flows across transmission networks. Electricity is unusual because, in most grid systems, it must be generated and consumed almost at the same time. Large batteries and other storage technologies are becoming more important, but the grid still depends heavily on real-time balancing. It cannot simply place excess electricity in a cupboard for later, next to spare light bulbs and optimism. This is where timing becomes essential. To understand what is happening across a large grid, operators need to know not only how much electricity is flowing, but how the electrical waves are behaving at different places. Alternating current has frequency, but it also has phase. Phase describes where a wave is in its cycle at a particular moment. Two waves may have the same frequency, but one may be slightly ahead or behind the other. Across a large grid, those tiny differences can reveal how power is moving and whether the system is stable. Phasor measurement units are one of the key technologies used to monitor this. A phasor measurement unit measures the voltage and current waves at a particular location, along with their timing. The important part is that measurements from different locations can be compared only if they share an accurate time reference. If one device measures a wave in one city and another device measures a wave hundreds of kilometers away, the comparison is meaningful only when both measurements are time-stamped with great precision. This is why synchronized timing is so valuable. Phasor measurement units often use timing signals traceable to satellite navigation systems, which themselves depend on atomic clocks. By attaching precise timestamps to electrical measurements, grid operators can see the grid almost as a single coordinated system rather than a collection of isolated measurements. They can compare distant waves, detect oscillations, observe stress, and respond more quickly to instability. A rough comparison may help. Imagine trying to understand a huge orchestra spread across an entire country. One violin section is in one city, the brass is somewhere else, the percussion is on a mountain, and the conductor has had a very difficult morning. To know whether the orchestra is playing together, it is not enough to hear each section separately. The timing between them matters. The grid is not music, of course, but it is a large connected system where rhythm, phase, and coordination make the difference between stability and confusion. Organizations such as the North American Electric Reliability Corporation help set and enforce reliability standards for the bulk power system in North America. National grid operators, transmission system operators, and regional reliability organizations around the world manage their own networks according to local rules, infrastructure, and demand patterns. The details vary from country to country, but the underlying need is shared. Electricity must be monitored and coordinated with care. This need is growing. Renewable energy sources such as wind and solar power bring major benefits, but they also change how grids are managed. Traditional power plants often use large rotating machines that naturally contribute inertia to the grid, helping resist sudden frequency changes. Wind turbines and solar panels connect differently, often through power electronics, and their output can vary with weather, daylight, and local conditions. This does not make renewable energy unmanageable, but it does mean grid operators need good measurement, forecasting, control systems, storage, and timing. Long-distance transmission adds more complexity. Electricity may travel across regions, borders, or entire countries, linking distant generators with faraway demand. Power flows can shift as weather changes, factories start up, homes heat or cool, and renewable production rises or falls. Demand itself has become more complex, shaped by air conditioning, data centers, electric vehicles, heat pumps, industrial loads, and millions of ordinary human decisions. A person turning on a kettle is not personally destabilizing the grid, thankfully, but millions of kettles, heaters, chargers, and machines together form a very real pattern. Precise timing helps turn that complexity into something visible. It allows grid operators to see changes as they move through the network. It helps identify faults, track disturbances, and understand whether different parts of the grid are staying synchronized. It supports protection systems, control rooms, planning models, and post-event analysis. When something goes wrong, accurate timestamps can help reconstruct the sequence of events, showing how a disturbance began and how it spread. Atomic clocks enter this story quietly. Most people do not imagine quantum physics when they plug in a lamp, yet the time references used in modern grid monitoring often trace back to satellite systems and national timing standards supported by atomic clocks. The same quantum regularity that defines the second can help electrical engineers compare waveforms across huge distances. Atoms help provide the time, and that time helps keep electricity orderly. This does not mean every wall socket is directly connected to a cesium clock in some dramatic way. The connection is more subtle and more interesting. Atomic time supports navigation satellites, time distribution systems, communication networks, and reference clocks. Those timing systems support phasor measurement units, control networks, and grid monitoring. The result is a layered structure where quantum precision contributes to very practical stability. The power grid is one of the clearest reminders that modern life depends on invisible coordination. Electricity feels simple when it works. It becomes noticeable mainly when it stops, when the lights go dark, the router sighs into silence, and everyone suddenly remembers how many things in the house are not actually candles. But most of the time, the grid remains steady because people, machines, measurements, and timing systems are constantly working together. Quantum time helps keep that hidden rhythm aligned. It supports the clocks that support the measurements that support the operators who keep electricity flowing. And in that quiet chain of dependence, atoms once again appear beneath everyday life, helping the modern world stay bright, balanced, and gently humming. Time feels as if it should be the same everywhere. 1 second here should be 1 second there. A clock on a desk, a clock in a pocket, a clock on a mountain, and a clock in orbit should all be measuring the same steady flow, as if time were a universal river moving calmly beneath everything. But Albert Einstein showed that reality is not quite so obliging. In the theory of relativity, time is not perfectly universal. It depends on motion and gravity. That does not mean time is imaginary, or that clocks can simply do whatever they like after a difficult morning. It means that the rate at which time passes depends on the path the clock takes through space-time. Two clocks can be built perfectly, started together, and later disagree, not because one is broken, but because they have experienced different physical conditions. This idea began with special relativity, published by Einstein in 1905. Special relativity deals with motion, especially motion at constant speed. One of its central results is that moving clocks tick more slowly relative to clocks at rest, from the viewpoint of an observer comparing them. The effect is called time dilation. At everyday speeds, this difference is far too small to notice. A person walking across a room does not return younger in any useful sense, although after a long enough walk they may return slightly more convinced they should have stayed seated. But at very high speeds, especially speeds approaching the speed of light, the effect becomes important. Particles moving rapidly in accelerators and cosmic rays entering Earth's atmosphere show time dilation clearly. Their internal processes appear to unfold differently because motion affects time. Special relativity does not say that one clock is secretly wrong. It says that time and space are linked, and different observers moving relative to one another can measure time differently. The old idea of one universal time ticking identically for the entire universe had to be replaced by something stranger and more precise. Then came general relativity, published in its full form in 1915. General relativity extended Einstein's ideas to include gravity. In this theory, gravity is not simply a force pulling objects together. It is connected to the curvature of space-time caused by mass and energy. Objects move through this curved space-time, and clocks are affected by it too. The practical result is gravitational time dilation. A clock deeper in a gravitational field ticks slightly more slowly than a clock higher up, where gravity is weaker. A clock closer to Earth's surface runs a little slower than a clock on a mountain. A clock in orbit farther from Earth's mass runs differently again. The effect is tiny, but it is real. This sounds almost dreamlike, but it has been tested many times. One important early test was the Pound-Rebka experiment at Harvard University in 1959. Robert Pound and Glenn Rebka measured the change in energy of gamma rays moving up and down in Earth's gravitational field. Their result confirmed a key prediction of general relativity. Gravity affects the frequency of radiation, which is closely related to the way clocks measure time. Another famous test involved Joseph Haffel and Richard Keating in 1971. They flew atomic clocks around the world on commercial airliners, travelling both eastward and westward, then compared them with reference clocks that had remained on the ground. The clocks differed by tiny amounts, in agreement with predictions from special relativity and general relativity. The experiment was not perfect by today's standards, but it was a striking demonstration that time differences caused by motion and gravity could be measured with real clocks in the real world. Modern experiments have gone far beyond this. Atomic clocks can now compare time differences caused by surprisingly small changes in height. Extremely precise optical clocks have measured differences in ticking rates over height changes small enough to make relativity feel less like an abstract theory and more like a feature quietly woven into the room. Time does not wait until black holes and distant galaxies appear before becoming strange. It is already strange on Earth, just very discreet about it. Atomic clocks made relativity practical because they are precise enough to reveal effects that ordinary clocks cannot see. A pendulum clock, a wristwatch, or a kitchen clock is not going to detect the difference between the floor and a table, but modern atomic clocks can measure time so finely that altitude, motion, and gravitational potential become part of the calculation. This matters enormously for satellite navigation. Satellites move quickly around Earth, so special relativity affects their clocks. They also orbit high above the surface, where Earth's gravity is weaker, so general relativity affects their clocks too. The two effects work in different directions, but together they must be corrected. Without these relativistic corrections, satellite navigation systems would drift badly. A map application would not merely become a little imprecise. Over time, it could guide people with cheerful confidence into entirely wrong places, which is not ideal unless the destination is somewhere else. Relativity also matters in laboratories. When national metrology institutes compare highly precise clocks, they must account for height differences. A clock in one building may not tick at exactly the same rate as a clock in another building at a different altitude. This is not a flaw in the clocks. It is a measurement of gravity's effect on time. This has led to the field of relativistic geodesy, where precise clocks can be used to measure differences in gravitational potential. Because a clock's ticking rate changes with height in Earth's gravitational field, clocks may help scientists study the shape of Earth, monitor sea level, compare elevations, and detect subtle changes in mass distribution. In this sense, a clock becomes more than a timekeeper. It becomes a sensor for gravity. That is one of the deepest surprises in quantum timekeeping. Atomic clocks do not merely keep time more accurately than older clocks. They reveal that time itself is part of the physical world. It responds to motion. It responds to gravity. It changes with height, speed, and the curvature of space-time. The modern clock, built from quantum transitions inside atoms, becomes a tool for seeing relativity. Tiny atomic rhythms expose the shape and motion of the universe around them. A clock is no longer just a device that tells people when to leave the house. It is a witness to space-time, quietly showing that time is not the same everywhere and never truly was. Cesium clocks change the meaning of time by tying the second to a microwave transition inside atoms. But precision timekeeping did not stop there. Once scientists had learned to use atoms as clocks, the next question was almost inevitable. Could an even faster atomic rhythm measure time even more finely? The answer led to optical atomic clocks. A cesium atomic clock uses microwave radiation to probe the transition that defines the present official second. Microwaves have very high frequencies compared with ordinary mechanical motion, which is one reason cesium clocks are so precise. But optical clocks use transitions at much higher frequencies still. These transitions involve light closer to the optical range, meaning frequencies associated with visible light or nearby parts of the electromagnetic spectrum. A higher frequency gives scientists many more cycles to count in each second, and in timekeeping more cycles can mean finer resolution. A simple comparison is a ruler. If a ruler has only large marks, it can still measure distance, but not with the finest detail. If it has many tiny marks, it can measure more precisely. In a similar way, an optical clock has a much faster rhythm than a microwave cesium clock. It offers a finer set of divisions for measuring time, not because time itself comes in little printed lines, but because the clock's reference frequency is so much higher. Optical clocks use atoms or ions with extremely narrow stable transitions. Some of the leading examples involve strontium, ytterbium, aluminium ions, and mercury ions. Different laboratories use different systems because each has advantages and challenges. Strontium and ytterbium are often used in optical lattice clocks. Aluminium ions and mercury ions have been used in highly precise ion clocks. The basic goal is always similar. Find a quantum transition that can be measured with extraordinary stability, protect it from disturbances, and compare it with other clocks so carefully that even tiny differences become meaningful. This work is carried out by major metrology laboratories and research institutions around the world. The National Institute of Standards and Technology in the United States has developed some of the most advanced optical clocks, including aluminium ion clocks and ytterbium lattice clocks. The Joint Institute for Laboratory Astrophysics, connected with the University of Colorado Boulder and the National Institute of Standards and Technology, has played an important role in optical clock research. The National Physical Laboratory in the United Kingdom, the Physikalische Technische Bundesanstalt in Germany, and other national metrology institutes have also helped push optical timekeeping forward. This is not a single laboratory race with one dramatic finish line. It is a global effort to refine time itself. To make these clocks work, scientists must quiet the atoms down. At ordinary temperatures, atoms move quickly. Their motion blurs measurements, shifts frequencies, and makes the clock less precise. Laser cooling solves part of this problem by using carefully tuned laser light to slow atoms. The idea sounds contradictory, because light usually feels like something that warms or illuminates. But photons carry momentum, and when atoms absorb and emit photons in just the right way, their motion can be reduced. The atoms become extremely cold, often only tiny fractions above absolute zero. Once slowed, atoms must often be trapped. In optical lattice clocks, lasers create a standing wave of light that acts like a delicate array of tiny holding places for atoms. The atoms are trapped in this optical lattice, arranged in a way that allows many atoms to be measured at once while reducing motion and other disturbances. It is a little like persuading a crowd of restless dancers to stand very still on an invisible staircase made of light. The image is odd, but the science is real. Ion clocks use a different approach. Instead of measuring many neutral atoms in an optical lattice, they may trap a single charged atom called an ion using electric fields. A single ion can be isolated extremely well, which reduces some sources of disturbance. The trade-off is that a single particle gives less signal than many atoms, so the engineering and measurement methods must be exceptionally careful. Both optical lattice clocks and ion clocks are powerful, but they solve the problem of precision in different ways. Another key technology is the frequency comb. Optical frequencies are so high that ordinary electronics cannot count them directly in a simple way. A frequency comb acts as a bridge between optical frequencies and microwave or radio frequencies that electronics can handle. It creates a set of evenly spaced frequency markers, like the teeth of a comb, allowing scientists to measure optical light with extraordinary accuracy. Theodor Hensch and John Hall shared the Nobel Prize in Physics in 2005, along with Roy Glauber, for work connected to precision laser spectroscopy and optical frequency combs. Without frequency combs, optical clocks would be far harder to compare, read, and connect to practical timekeeping. Optical clocks are now so precise that they can outperform the best cesium standards in stability and accuracy. Some are sensitive enough to detect gravitational time differences over very small height changes. Move one clock slightly upward, and because it is in a slightly weaker gravitational field, it ticks at a slightly different rate. That is not a flaw. It is general relativity becoming visible through timekeeping. This sensitivity is both powerful and inconvenient. An optical clock can be so precise that the exact height of the laboratory matters. The gravitational environment matters. The temperature of nearby surfaces matters. Magnetic and electric fields matter. Tiny shifts that once would have been ignored now become part of the measurement. Better clocks do not make the universe simpler. They reveal more of its small print. Because optical clocks can exceed cesium clocks, scientists are preparing for the possibility that the second may eventually be redefined. The official second is still based on cesium-133, but optical clocks are strong candidates for the next generation of time standards. Before that change can happen, laboratories must compare optical clocks reliably, understand their uncertainties, choose the best practical definition, and ensure that the new standard can be reproduced internationally. This is how timekeeping advances, not by throwing away the past, but by building on it. Cesium clocks gave the world a quantum definition of the second. Optical clocks may give the world an even sharper one. The rhythm of modern time is moving from microwaves toward light, from already astonishing precision toward something even more exact. And somewhere in these chilled atoms, trapped ions, lasers, and frequency combs, the next version of the second is quietly being prepared. Time, which once lived in shadows and pendulums, is now being refined in the colour of atomic light. A clock seems like a device for measuring time, which is already impressive enough. But the most precise clocks have begun to do something stranger. They can measure height. Not height in the ordinary sense. With a tape measure, a ruler, or someone standing against a doorframe while a pencil mark slowly records the rise of childhood. These clocks measure height through gravity. More exactly, they measure differences in gravitational potential, which is the energy landscape created by Earth's gravity. A clock in one place can tick at a slightly different rate from a clock somewhere else, and that difference can reveal where the clock sits in Earth's gravitational field. This idea is called relativistic geodesy. Geodesy is the science of measuring Earth's shape, orientation, gravitational field, and changes over time. It is the science behind maps, surveying, sea level measurement, satellite positioning, and our understanding of Earth as a real, uneven, moving planet rather than a perfect classroom sphere. Relativistic geodesy uses Einstein's general theory of relativity and extremely precise clocks to measure differences in height and gravity. The principle comes from gravitational time dilation. According to general relativity, a clock deeper in a gravitational field ticks slightly more slowly than a clock higher up, where gravity is weaker. Near Earth, this means a clock at a higher altitude ticks a little faster than a clock closer to sea level. The difference is tiny, but it is not imaginary. It is a real physical effect, and atomic clocks have become sensitive enough to measure it. A simple way to picture it is to imagine time as being very slightly compressed, lower down in Earth's gravity. This is not a perfect image, but it helps capture the idea. A clock closer to Earth's centre sits deeper in the gravitational field, and its seconds pass a little more slowly compared with a clock higher up. Climb a mountain, and time runs very slightly faster. Not enough to help anyone age out of paying bills, sadly, but enough for the best clocks to notice. For older clocks, this effect was far too small to use in practical measurement. But optical atomic clocks have changed the scale of what can be detected. Some optical clocks are precise enough to measure time differences linked to height changes of only a few centimetres under carefully controlled conditions. That is an extraordinary thought. A clock can, in principle, sense that it has been lifted slightly higher because time itself ticks differently there. This turns timekeeping into a tool for Earth science. Traditionally, height is measured using surveying, satellite navigation, levelling, radar, and models of Earth's gravity field. These methods are powerful, but Earth is complicated. The planet is not a smooth ball. It bulges at the equator, has mountains and trenches, contains moving water, shifting ice, flowing rock, dense and less dense regions underground, and oceans that do not sit on a simple mathematical surface. Even sea level is not one perfectly even shell around the planet. Gravity shapes it. Relativistic geodesy offers another way to connect height with gravity. If two clocks are compared and one ticks faster than the other, that difference can reveal a difference in gravitational potential. Since gravitational potential is linked to height in Earth's field, clock comparisons can help determine height differences. This does not replace every other method, but it adds a powerful new approach, especially when combined with satellite geodesy, gravimetry, and traditional surveying. Scientific bodies such as the International Association of Geodesy are concerned with the global systems used to measure Earth, including reference frames, gravity field models, and height systems. National mapping agencies, geophysical institutes, metrology laboratories, and organisations involved in Earth observation all have a stake in this kind of measurement. The work sits at the boundary between timekeeping, relativity, surveying, and planetary science. One possible use is sea level monitoring. Sea level is not just about how high the ocean appears on a coastline. It is connected to Earth's gravity field, ocean circulation, land movement, ice melt, and climate change. Precise clocks could help improve the reference systems used to compare heights across large distances. If one region of land is slowly rising or sinking, or if ocean levels are changing relative to the land, better height measurement can help scientists separate the different causes. Volcanic regions are another possible application. Before and during volcanic activity, magma can move beneath the surface, changing the shape and mass distribution of the ground. Scientists already use instruments such as satellite radar, tilt meters, seismometers, and gravity meters to monitor volcanoes. In the future, networks of highly precise clocks might contribute by detecting changes in gravitational potential linked to swelling ground or underground mass movement. A clock would not replace a volcano observatory, but it could become one more quiet witness to the planet's restlessness. Groundwater is also important. Water moving underground changes mass distribution, and large changes in groundwater storage can subtly affect gravity. This matters for drought monitoring, aquifer management, agriculture, and climate science. If precise clocks can help detect or support measurements of gravitational changes, they may contribute to understanding where water is being stored, lost, or shifted beneath the surface. Ice sheets offer another powerful example. Greenland and Antarctica contain vast masses of ice. As ice melts, flows, or accumulates, it changes local gravity and contributes to sea level rise. Satellites already measure ice sheet mass changes, but future clock-based geodesy could provide complementary measurements, especially as portable optical clocks improve. Timekeeping may become part of the toolkit for watching frozen landscapes change. The same idea could apply to subtle shifts in Earth's gravitational field caused by tectonic movement, ocean loading, seasonal water storage, or changes in large infrastructure systems. Earth is not still. It breathes in slow geological and environmental motions, mass moves, rock flexes, water flows, ice melts and grows, air presses and shifts. The planet changes shape and gravity in ways that are often too small for human senses, but not too small for careful instruments. This is where quantum time becomes more than timekeeping. An atomic clock begins with a quantum transition inside an atom. That transition defines a rhythm. But when the clock is precise enough, the rhythm becomes sensitive to the world around it. It tells not only how much time has passed, but how gravity is shaping that passage. A clock that can feel height is one of the gentlest and strangest achievements of modern physics. It links the smallest reliable rhythms inside atoms with the vast uneven body of Earth. It shows that time is not merely a background against which the planet moves. Time is part of the measurement of the planet itself. So quantum clocks do not only keep civilization synchronized, they can help read the hidden shape of the world beneath our feet. They turn seconds into sensors, and in doing so, they make Earth's gravity quietly audible through the ticking of atoms. Atomic clocks began as instruments for keeping time, but the better they become, the more they turn into something else as well. They become instruments for testing reality. That may sound like a dramatic job description for a clock. A clock on a wall is usually expected to do one thing: move steadily enough that nobody burns dinner or misses a train. But the most precise atomic and optical clocks are not ordinary timekeepers. They are sensitive scientific instruments. They can compare tiny differences in frequency so carefully that they allow physicists to ask whether the laws of nature are behaving exactly as expected. At the heart of this idea is a simple question with enormous consequences. Are the constants of physics truly constant? A fundamental constant is a number that appears to be built into the structure of physical law. These constants help determine how particles interact, how atoms form, how light behaves, and how matter holds together. One important example is the fine structure constant. The fine structure constant describes the strength of the electromagnetic interaction, the interaction between electrically charged particles and light. It helps shape atomic spectra, chemical behaviour, and the detailed structure of matter. The fine structure constant is not a household name, which is probably fair. It has not done much to improve its public relations, but it is deeply important. If its value were different, atoms would behave differently. The patterns of light absorbed and emitted by atoms would shift. Chemistry would change. The familiar structure of matter would not be quite the same. So when scientists ask whether the fine structure constant has always had the same value, they're not asking a decorative question. They are testing whether one of the quiet ingredients of reality has remained stable across time and space. Atomic clocks are useful in this search because different atomic transitions depend on physical constants in different ways. A cesium clock, a strontium optical clock, an ytterbium clock, an aluminium ion clock, and a mercury ion clock do not all respond identically to possible changes in the underlying constants of nature. If two different clocks are compared over long periods, and their frequency ratio remains unchanged, that supports the idea that the relevant constants are stable. If the ratio were to drift in a way that could not be explained by known effects, it might point toward new physics. The basic method is beautifully patient. Scientists compare one precise clock with another, again and again, searching for the tiniest signs of change. The clocks are not simply being used to tell the time. They are being used as different kinds of atoms listening for whether the rules of physics are holding steady. If nature were subtly changing its tune, different clocks might notice the change in slightly different ways. Institutions such as the National Institute of Standards and Technology in the United States, the National Physical Laboratory in the United Kingdom, the Physikalische Technische Bundesanstalt in Germany, and other national metrology institutes have contributed to this kind of work. University research groups and laboratories connected with precision spectroscopy also play a major role. The European Laboratory for Particle Physics, better known as CERN, is most famous for particle accelerators, but it also belongs to the wider scientific effort to test fundamental physics with extraordinary precision. Across these fields, the goal is not to assume that known physics is wrong. It is to check with increasing care whether it remains right. Precise clocks can also test relativity. Albert Einstein's general theory of relativity predicts how gravity affects time, and atomic clocks can measure those effects with remarkable sensitivity. If two clocks are placed at different heights, they tick at slightly different rates because they sit at different gravitational potentials. If clocks are compared while moving, special relativity must also be considered. These effects have been confirmed many times, but better clocks allow more demanding tests. They help scientists ask whether relativity continues to hold at finer and finer scales of measurement. So far, relativity has done extremely well. This is important to say clearly. Precision clocks have not casually knocked Einstein off the shelf. They have mostly confirmed that the theory works with astonishing accuracy. But each better test narrows the space for possible deviations. If there is a deeper theory that modifies relativity under certain conditions, precise measurements help show where it cannot hide. Atomic clocks are also being explored in searches for dark matter. Dark matter is the unseen form of matter inferred from its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. Scientists know it behaves gravitationally, but its particle nature remains unknown. Some theories suggest that certain forms of dark matter could interact very weakly with ordinary matter and cause tiny temporary changes in fundamental constants. If that happened, atomic clocks might detect small shifts in their frequencies. One idea is that Earth could pass through a region or field associated with dark matter, and different clocks might respond with a tiny correlated disturbance. Another possibility is an oscillating dark matter field that would cause clock frequencies to vary in a repeating pattern. These are careful scientific searches, not claims that clocks have already found dark matter hiding under the laboratory floor with a clipboard. The point is that clocks are now sensitive enough to take part in the hunt. This is the grounded beauty of precision physics. Most of the time, the result is not a dramatic discovery, it is a tighter limit. Scientists say, in effect, if new physics exists in this particular form, it must be smaller than this, weaker than this, rarer than this, or hidden in a different place. That may sound less exciting than a sudden breakthrough, but it is how science often advances. The map of what is possible becomes more precise. Atomic and optical clocks therefore sit at a remarkable crossroads. They support navigation, communication, finance, power grids, and global timekeeping. But they also test whether the fine structure constant changes, whether relativity behaves exactly as predicted, and whether dark matter might leave faint fingerprints in the ticking of atoms. None of this means established physics has been overturned. The standard theories remain extraordinarily successful. Quantum mechanics, relativity, and the standard model of particle physics have survived a century of demanding tests. But scientists know these theories are not the final word on everything. Gravity and quantum physics are not yet unified. Dark matter remains unidentified. Dark energy remains deeply mysterious. The early universe still raises questions that current theories do not fully answer. So the search continues in tiny ticks. A clock becomes a way of asking whether nature is truly constant. A frequency comparison becomes a test of physical law. a quiet atom in a laboratory becomes part of a much larger investigation into the structure of reality. And once again, the smallest rhythms in matter reach outward, not only keeping the modern world in time, but helping science listen for anything in the universe that may not be ticking exactly as expected. The most precise atomic clocks in the world are not usually the sort of objects that can be casually packed into a bag. Many of them live in carefully controlled laboratories, surrounded by lasers, vacuum chambers, electronics, temperature controls, vibration isolation, magnetic shielding, and people who understand exactly which cable should not be touched. They are magnificent instruments, but they are not convenient travel companions. This creates a practical problem. The best clocks are often large and delicate, while the world that needs precise timing is large, messy, mobile, and not always kind to laboratory equipment. A national metrology laboratory can maintain an exquisite optical clock under carefully controlled conditions. But a ship at sea, a remote telecom station, an aircraft, an emergency response unit, an underground tunnel, or a piece of military equipment may need stable time in places where a full laboratory clock would be impossible. So another branch of atomic timekeeping has become increasingly important: portable atomic clocks. The purpose of a portable atomic clock is not necessarily to match the finest clocks in the world. That would be like asking a bicycle to compete with a spacecraft, because both technically involve motion. The goal is different. Portable atomic clocks bring stable timing into places where ordinary clocks may drift too much, where satellite signals may be unavailable, or where local systems need to keep working independently for long periods. One important example is the chip-scale atomic clock. A chip-scale atomic clock is a miniaturized atomic clock designed to be small, low power, and practical for use outside large laboratories. It still relies on an atomic transition, often using rubidium or cesium vapor, but the system is built into a compact package. Instead of a large beam tube or an elaborate fountain apparatus, a chip-scale atomic clock uses tiny components, including a small vapor cell, compact optics or microwave systems, electronics, and a feedback mechanism. The basic principle remains familiar. The device uses atoms as a reference. It applies a signal, watches how the atoms respond, and adjusts its own oscillator to stay locked to the atomic transition. What changes is the scale and the engineering. The clock must be made small enough, robust enough, and energy efficient enough to work where a laboratory instrument could not. These clocks are not as accurate as the best primary standards or advanced optical clocks, but they are far more stable than many ordinary compact timing devices. That makes them valuable in systems that need reliable time over minutes, hours, days, or longer, especially if outside timing signals disappear. A quartz oscillator may drift. A portable atomic clock can hold time much more steadily. This matters in navigation. Many navigation systems depend on signals from satellites, such as GPS, Galileo, GLONASS, or Beidou. But satellite signals can be weak, blocked, jammed, reflected, or unavailable. Tall buildings, tunnels, mountains, dense forests, underwater environments, underground facilities, and hostile conditions can all make satellite navigation difficult. A portable atomic clock cannot magically replace all satellite navigation by itself, but it can help a system keep accurate time when external signals are interrupted. Stable timing supports inertial navigation systems, communications, and position estimates until reliable external updates return. Defense applications are one reason compact atomic timing has received major investment. The Defense Advanced Research Project Agency in the United States has supported work on chip-scale atomic clocks and other portable precision timing technologies. In defense settings, Systems may need to operate when satellite signals are denied or deliberately interfered with. Reliable timing supports communications, radar, navigation, electronic systems, and coordination between units. In those conditions, time is not a luxury. It is part of resilience. Telecommunications also benefits from portable and distributed atomic timing. Networks need synchronization to organize signals, manage data, coordinate mobile base stations, and maintain service quality. In many places, timing can be distributed through satellite signals or fiber networks. But local atomic clocks can provide backup and stability when those references are disrupted. A telecom site with a stable local clock can keep operating more reliably through interruptions, rather than immediately losing coordination like a choir whose conductor has briefly wandered off to look for biscuits. Emergency response is another practical area. During disasters, infrastructure can be damaged. Satellite signals may be degraded, power systems may be unstable, and communication networks may be under strain. Portable timing devices can help support temporary networks, field communications, navigation, and coordination. In those situations, the goal is not record-breaking precision. It is dependable timing under difficult conditions. Underwater and underground environments make the need even clearer. Satellite navigation signals do not penetrate deeply underwater, and they may be unavailable in mines, tunnels, caves, bunkers, or underground transport systems. Submarines, underwater vehicles, drilling operations, underground mapping teams and rescue crews may all need timing systems that continue working without direct access to the sky. Stable clocks help navigation systems estimate movement and maintain coordination when external references cannot easily reach them. National metrology institutes still play an important role in this world. Institutions such as the National Institute of Standards and Technology, the National Physical Laboratory, and the Physikalische Technische Bundesanstalt help develop, compare, and refine precision timing technologies. Industrial research groups also matter because turning laboratory ideas into rugged, manufacturable devices is its own scientific and engineering challenge. A clock that works beautifully on a quiet optical table may need serious redesign before it can work in a vehicle, a field station, or a piece of network equipment. Portable atomic clocks show that quantum timekeeping is not only about chasing the most perfect second in the most controlled laboratory. It is also about carrying useful stability into the real world. A compact clock may not be the most accurate clock ever made, but it can be accurate enough, stable enough, and practical enough to make systems more reliable. That is often how technology changes civilization. Not all at once, and not always in dramatic visible form. Atomic time began in specialized laboratories with delicate instruments and carefully prepared atoms. Over time, it spread outward into satellites, telecom networks, data centers, power systems, vehicles, field equipment, and compact devices. It became less visible precisely as it became more useful. The quiet trend is clear. Atomic time is no longer only something maintained in national laboratories and shared through global standards. It is moving into smaller systems, distributed networks, portable equipment, and places where ordinary clocks may not be steady enough. The quantum rhythm that once seemed like a laboratory achievement is becoming part of the practical machinery of the world, and perhaps that is the real sign of success. The best technology often disappears into reliability. It stops feeling extraordinary because it works. Somewhere inside a small device, atoms respond to carefully tuned signals, a tiny clock corrects itself, and a system far from the laboratory keeps its place in time. The modern world often looks as if it runs on visible things. It runs on roads, cables, satellites, power stations, servers, ships, aircraft, phones, factories, laboratories, and millions of small screens glowing in pockets and homes. It runs on energy because nothing moves without it. It runs on materials because every machine has to be made from something. It runs on information because messages, measurements, payments, maps, and instructions are constantly moving from one place to another. But beneath all of that, the modern world also runs on agreement. It needs agreement about when things happen. That may sound modest compared with electricity, steel, silicon chips, radio signals, or the vast machinery of global trade. But timing is one of the quiet foundations beneath them all. A satellite signal is useful only if its timing can be trusted. A bank transfer is meaningful only if its sequence is known. A power grid remains stable only if distant electrical waves can be compared. A telecommunications network works only if its devices stay synchronized. A laboratory measurement becomes part of science only when it can be compared with other measurements, under shared standards, across time and distance. Modern civilization is not just a collection of machines, it is a collection of coordinated machines. Coordination needs clocks. That is why quantum timekeeping matters so deeply. Atoms provide stable, repeatable transitions that human technology can compare, count, and share. When an atom changes between specific energy states, it is not behaving like a spring, a gear, or a swinging pendulum. It is following the rules of quantum physics. Those rules may seem strange, but they are also astonishingly reliable. The transitions occur at frequencies that can be measured again and again in different laboratories in different countries using carefully built instruments. This is the quiet power of atomic clocks. They turn the consistency of atoms into a shared rhythm for the world. The second is no longer defined by the uneven turning of Earth. It is tied to the transition inside cesium 133 atoms, coordinated through the international system of units, and maintained by organizations such as the Bureau International de Poids et Mesures. From that definition, time flows outward into national laboratories, satellite systems, fiber networks, telecom equipment, servers, receivers, power grid instruments, and countless systems that depend on synchronization. Satellite navigation is one of the clearest examples. A phone can estimate position because signals from satellites arrive with carefully measured timing. GPS, Galileo, GLONASS, and Beidou all depend on atomic clocks and coordinated time. The receiver is not simply asking where the satellites are, it is asking when their signals were sent and how long those signals took to arrive. Because radio signals travel at the speed of light, even a tiny timing error can become a large position error. The blue dot on a map is really a triumph of clocks. Telecommunications depends on the same hidden discipline. Phone networks, fiber optic links, data centers, and cloud systems need shared timing to organize communication. Computers use methods such as the network time protocol and the precision time protocol to compare and correct clocks across networks. Messages feel instant, but digital systems are built from sequences. One event must be known to happen before another. A call connects, a file updates, a video streams, and a server responds because machines keep agreeing on the order of events. Finance depends on that order too. A payment is not just a number moving from one place to another, it is a record in time. Banks, payment networks, stock exchanges, clearing houses, and trading systems need accurate timestamps to know when instructions arrived, when trades occurred, when balances changed, and when settlements were made. Without reliable time, financial records become harder to trust. Money in the digital age is not only value, it is value arranged in sequence. Power grids depend on timing in a more physical way. Alternating current systems must maintain frequency, phase, and balance across huge networks. Grid operators use carefully timed measurements to understand how electrical waves are behaving in different places. Phasor measurement units compare voltage and current waves across distant parts of a grid, often relying on timing ultimately connected to atomic clocks and satellite signals. The lights stay on because electricity is not only generated, it is coordinated. Scientific laboratories depend on precise time because measurement itself depends on shared standards. National metrology institutes compare clocks, refine uncertainties, and help maintain the time references used by science and industry. Optical clocks, using atoms and ions such as strontium, ytterbium, aluminium ions, and mercury ions, are pushing timekeeping beyond the cesium clocks that define the present second. These clocks are so precise that height, gravity, temperature, and motion all become part of the measurement. That precision turns clocks into scientific sensors. Relativistic geodesy uses the fact that clocks tick differently, at different gravitational potentials. A clock at a slightly higher altitude ticks a little faster than one lower down. With sufficiently precise clocks, timekeeping can help measure height, gravity, sea level change, ice sheet behaviour, groundwater movement, and the hidden shape of Earth itself. A clock becomes a way of reading the planet. Even fundamental physics listens to these tiny ticks. Atomic and optical clocks can test whether constants such as the fine structure, constant, remain stable. They can test predictions of Albert Einstein's special relativity and general relativity. They can help search for possible interactions with dark matter. So far, these clocks have not overturned established physics. Instead, they have done something just as important. They have made the test sharper, narrowing the spaces where new physics might hide. This is the strange beauty of quantum time. Daily life feels solid and ordinary. A phone buzzes, a kettle boils, a payment clears, a map loads, a train leaves, a light turns on. None of this feels especially quantum. Most people do not look at a working internet connection and think of cesium atoms, microwave transitions, optical lattices, or frequency combs, which is probably healthy. Life is already quite busy. Yet beneath that ordinary surface, the modern world is tied to quantum rules. The most reliable clocks are not based on large visible motions, but on tiny atomic transitions. Atoms do not keep the world running by pushing wheels or turning gears. They keep it running through hidden coordination. Their regularity allows human systems to compare, correct, and trust time across the planet. That is why the title is more literal than it first appears. Atoms keep the modern world running because they give civilization a shared rhythm. They help satellites locate us, networks connect us, markets record us, power grids support us, laboratories measure the world, and scientists test the laws of physics. They sit beneath the visible machinery of daily life, not as decoration, but as part of the infrastructure. Every phone signal, every satellite correction, every internet transaction, every laboratory comparison, every synchronized system carries a faint connection to atoms ticking in carefully guarded rooms around the world. The tick is not loud. It is not visible. But it is there, steady and precise, quietly helping the world move together through time. Atoms keep the modern world running because their quantum behaviour gives civilization something quietly precious, a shared and stable way to measure time. Not a rough sense of time, not a shadow moving across stone, not the slightly uneven turning of Earth beneath the stars, but a rhythm so consistent that satellites, laboratories, power grids, financial systems, communication networks, and scientific instruments can all lean on it. The journey began with the oldest forms of timekeeping, when people watched the sun, followed shadows, measured flowing water, burned candles, and divided the day using the best regular processes they could find. For most of human history, Earth itself seemed to be the natural clock. Its rotation gave the day, its orbit gave the year. The sky provided a grand and ancient rhythm. But as science and technology became more precise, it became clear that Earth was not steady enough to define time at the deepest level. The planet wobbles, slows, shifts, and changes, which is perfectly acceptable behaviour for a living world, but less ideal for precision measurement. So time moved inward, from the heavens to the atom. Cesium-133 became the foundation of the official second, using a specific transition between hyperfine energy levels. Atomic clocks learn to test atoms with microwaves, detect their response, and lock onto their natural quantum frequency. International time standards emerge from many clocks compared across national laboratories, coordinated through organisations such as the Bureau International des Poids et Mesures. No single clock ruled the world. Instead, time became a carefully maintained agreement. From there, atomic time spread quietly into daily life. Satellite navigation depends on precise timing to calculate position. Internet systems, cloud services, and telecommunications depend on synchronized clocks to keep digital events in order. Financial markets and payment networks need trusted timestamps. Power grids rely on timed measurements to monitor frequency, phase, and stability. Relativity showed that clocks tick differently with motion and gravity, and atomic clocks made those differences practical enough to measure. Optical clocks now push precision even further, allowing time itself to become a tool for sensing height, gravity, Earth's shape, and perhaps even tiny hints of new physics. Quantum timekeeping is not abstract speculation. It is real infrastructure. It sits beneath navigation, communications, science, finance, electricity, and the ordinary coordination of modern life. And that is the quiet wonder beneath every second. Something almost impossibly small helps organize something almost impossibly large. Tiny atomic transitions hidden far below human sight help hold together the timing of a planet. Every ordinary second is supported by an extraordinary agreement between nature, measurement, and human cooperation.